All right, so in this clip, we're going to look at how to set up an integral for finding the surface area of one of these parametrized surfaces that we've been putting so much time and effort into constructing. So just going back to my map of sigma and what sigma looks like. So here we're mapping from the UV plane over into the XYZ plane. And if I look at what's going on with a little patch right here, so this is a little rectangle in the UV plane with side lengths of delta U and delta V. How is that distorted under the mapping, the parametrization? Well, there's going to be some change in area. So we have some parallelogram over here, and the vectors that are spanning its sides are going to be the partials with respect to U and V. So what that's telling us then is that we're going to be looking at the area of S as being the integral over the parametrization domain of the magnitude of sigma U cross sigma V with respect to area. Now, if you remember, sigma U cross sigma V is going to be a vector that is perpendicular to both of them, and the length of it is going to be equal to the area of that blue parallelogram. So that's exactly why that's the thing that we need to be integrating, that area. And so remember here, sigma is sigma of U and V is going to have X, Y, and Z components, and each of those is going to be a function of U and V. So when I talk about sigma sub U, I'm talking about dx, du, dy, du, and dz, du, and similarly for sigma v. Okay, so let's do an example. We'll do the sphere because this will be nice and familiar. So let's see, in this case, remember we found our parametrization to be given by, let's see, we had A sine phi cosine theta, A sine phi sine theta, and then A cosine phi. And then this was for phi going halfway around, starting at the top and going to the bottom, and then for theta going all the way around. Okay, so again, this is just like spherical coordinates, except we're not doing the solid object, just the surface of it. So instead of having a row that varies through an interval, we just have a fixed value A, and that's going to be our radius. So let's see, so when I do the partials here, sigma phi, this is going to be, let's see, so we've got A cosine phi cosine theta, and then we've got A cosine phi sine theta, and then we've got minus A sine phi. And for sigma theta, we have minus A, let's see, so sine phi sine theta, and then A sine phi cosine theta, and then we have 0 because there's no theta in the function for Z. So now we can go ahead and do the cross product. So we've got sigma phi cross sigma theta is going to be given by some determinant where in the first column for I we have A cosine phi cosine theta and minus A sine phi sine theta. And then in the next column for j hat we've got let's see, A cosine phi sine theta and A sine phi cosine theta. And then for k we have minus A sine phi and 0. And so when I do this cross cross product. I'll save you the tedium and just write out the answer. We've got a squared sine squared phi cosine theta in the first coordinate, and then minus a squared sine squared phi sine theta in the second, and then a squared sine phi cos phi in the last one. So now when I go to find the magnitude of this sucker, I'm going to have to square each of those things. So we have a to the fourth, good lord, sine to the fourth phi cosine squared theta plus a to the fourth sine to the fourth phi sine squared theta plus a to the fourth sine squared phi cosine squared phi. And then you can probably smell what's going to happen next. We're going to have some massive simplification. Good God, I hope so, right? So let's see. So first off, there's a common factor of a to the fourth all the way through, so I can pull that out as a squared. And then if you look at what's going on here, this and this are the same. So if I factor out that quantity from those two, I'm left with cosine squared plus sine squared, which equals 1. So this is just going to be, I've already got the a, sine to the fourth phi, plus sine squared phi cosine squared phi. And then this one here, actually, if you squint your eyes, let's see, I can rewrite this as sine squared phi squared, right? And then I've got that there's a sine squared phi common to both of these, so I can factor that out, and I'm left with another Pythagorean's theorem. And so then I can just pull out that sine, and I end up with a squared sine phi, which totally should be familiar to you because of what you know about the Jacobian of spherical coordinates, right? Okay, so now we're ready to go ahead and figure out what the area of this sphere is. So we go from 0 to 2 pi, 0 to pi, a squared sine phi d phi d theta. And so the neat thing about this is that you can see also, if you didn't want the area of the entire sphere, but just maybe some section of the northern hemisphere or something like that, you would just need to change these bounds appropriately, and you could now measure the area of that region. Say if you want to find the area of North America or something. Okay, so then this one is, and now we can Fubinate, apply the Fubini Theorem, and we got rectangles and rectangles and rectangles. So this is, let's see, with respect to theta, there's just 1. And then with respect to phi, we have sine phi d phi. And the whole thing boils down to, let's see, a squared times 2 pi from the thetas times minus cosine of pi minus negative cosine of 0. So that's 1 plus 1. So that's 2, and we have 4 pi a squared. There is our lovely little answer.